In our last example, we're asked to find the complex zeros of this given function, m of x, which actually isn't a quadratic function, since in this case, this is a degree 4 polynomial. However, for a polynomial of this type, we can use the methods that we've been using so far to still find zeros. We can start by factoring this given function using difference of squares to get t squared minus 64 times t squared plus 64. We can then further factor t squared minus 64 to get t plus 8, t minus 8, but we don't have any factoring techniques to factor t squared plus 64, so we'll leave that as is for now. What this does tell us is that we can already identify two zeros of this function, which would be 8 and negative 8, which we can identify from the first two binomial factors. But then, to consider t squared plus 64, we'll have to set that equal to 0. Subtract 64 to the other side and take the square root of both sides to get t is equal to plus or minus 8i. So that gives us our two remaining zeros, 8i and negative 8i. It also allows us to revisit our factored expression. We had already factored this expression as t plus 8, t minus 8, and up until now we haven't had a method for factoring an expression like t squared plus 64. But through the processes we've established now, we can come up with the two zeros for that portion of this function, meaning we can express t squared plus 64 as t plus 8i times t minus 8i. So one benefit of being able to come up with these complex zeros is that we can now come up with these complex factorizations of polynomial functions that previously we would not have been able to fully factor. Or at least not easily. In example 6, for instance, while we only had real solutions here, we can now represent this in a factored form as the quantity x minus 3 plus 2 root 5 and x minus 3 minus 2 root 5. We can represent the original expression that we had in example 5 now as x minus 2 plus 2 root 6 times the quantity x minus 2 minus 2 root 6. In example 4, we could use our two complex roots to write this as x minus 7 plus 4i times the quantity x minus 7 minus 4i. And in example 3, we could factor this as x minus 10i times x plus 10i. So this process of finding complex zeros allows us to identify the two values for a quadratic function that when substituted in will give us a function value of 0, and also allows us to write either these complex factorizations or, in the case of example 5 and 6 where we had real roots, just more complicated factored expressions that would be harder to achieve by applying the AC method or any other technique.